All right. So I'm going to be talking about our work on GHC and compiling Haskell, and in the optimizer in particular, the core-to-core pipeline. And first, we're going to talk about what's come before. There is CPS has been used a lot for compilers, and it helps with many optimizations, but it has some costs. Not everyone uses it, and was discovered back in the early 90s was that you don't necessarily have to go with CPS in order to get some of the benefits. You can reason using CPS and yet do some of those same optimizations on direct style code, and this is of course ANF. Was born from this, but then there are still some blind spots we've found. You are losing something, and here's an example. So we have a function like this where you have the inner loop, the find loop. It's definitely going to return either just or nothing. It's going to go to a known branch, and we will know, you can see which branch it's going to go to. Is this going to return true or false? Still, there's always that actual just or nothing object anyway. It's always allocated, or at least it exists as a value. At the very least, it has to. Just is born, changes control flow, is forgotten. So what we've done is we've extended this sort of ANF concept so that we can deal with that, and it has an effect in a couple lucky cases where we just don't need to do any allocation anymore. Obviously that was a very lucky special case, but so yes, so we're going to how that happens. So as I said, unoptimized code often creates these values that just exist very briefly and then aren't seen again. And here's, Booleans do this all the time. They don't end up on the heap, but they, it's still sort of wasted energy putting them somewhere. If code like this, just make a decision based on what a function returns. If we expand on what that function does, you can see, it's just doing its own little if. And so you have you're doing a case analysis on a case analysis, then someone ends up returning a value, someone else ends up consuming it. And so of course, this is why we have the case of case transform, as it's called. We say, well, this is silly. We sort of flatten everything out, and we say, you pull the context, the outer context, into each branch. Now there are issues of code duplication here. I'm going to sort of hand wave, and in many cases like this one, things work out fine because you do the known case, and you end up with this nice function, which is sort of what you might have wanted to write. And so yes, and this is routine. This is this is called by GHC the case of case transformation, and it's been done many times before. So it's old hat. But back to our recursive function, this gets trickier. We would like to take our case here and kind of pull it into the branches, but there's nothing that lets us do that. The transform doesn't do that, and so we will produce a value, a just or nothing value, consume it, and it's tantalizing because you can see, by looking at it, which branch it's going to go to. So one thing you might try doing is saying, okay, we're going to do some specialization. We're going to say, reproduce this function sort of with this call site there. Make a special find prime so that we can then add the call site, add the context to it. And now we have case of case happening, and life is grand, except now what do we do with that call site? Now we end up with the same sort of issue. We don't have any traction. So, we'd like to find something better. So as I said, we're going to think about doing these, well, what would continuation passing style do? And so we first say, well, what would this example look like in CPS? Going back to the half thing, it says, well, this ends up being this obvious red X where you have something that's going to produce the true or the false, and it's getting as its continuation the thing that's going to do the case analysis. And I'm sort of assuming that many things are kind of primitive operations and don't get CPS'd here. So the arithmetic, just to keep it on one slide. But at any rate, as I said, that's just a beta red X. All you end up doing is same beta reduction we would like to do otherwise. We call it here an administrative reduction, and you end up with the lovely if true and if false branches, so that it just the known case takes care of the rest. And so yes, and so that hence we see that the CPS is has the right idea, but if we don't want to use it, then the good news for us is that there exists ANF, that you perform all the administrative reductions you would be doing if you had it in CPS, but you just use the original lambda terms, and in fact the original formulation is you translate to CPS, do the administrative reductions, and then translate back, and then we show that if you were to do that, then you would end up making the same administrative reductions. The sort of ANF normalization steps of what would happen if you just compose those 3 steps. And so yes, the slogan here is to think in CPS but work in ANF. Right? The actual code you write will work on lambda terms, but when we reason about things, we can use the richness of CPS and sort of the having context as a thing we can have our hands on. So, back to the tougher example. Thinking in CPS means we have this function where now we have a couple of continuations running around in our code, but there's nothing actually this time kind of pops out. There aren't any beta red X's waiting for us to combine them, so this is already kind of normalized. But we can still see some other things. I mean, there are other things we can do in CPS that become kind of obvious. For instance, this K1 argument here is always known. Right? We know it's this case analysis to begin with, and then in the recursive call, it just gets passed back. And so, we can do something quite standard called the static argument transformation, where we now say, okay, fine, we pull out the non-varying argument into a separate argument, and now we just, the inner loop can just keep running as an inner loop. And now we just have the one occurrence of the argument there. And now when we inline the only instance of find, we end up here, where now we just have the one loop again, and we just have the one instance of the continuation, and effectively we've done what's called quantification, where we've taken a function and realized that it's always called with the same context, and we've said, well, wait, we can just write in that context. And then because find prime here is effectively just a continuation itself, it's sometimes called quantification. And it's not too hard to do, but obviously it's something you want to be in CPS to do it. It only makes sense in CPS. And then of course K1 was a very, is not a large function. We can certainly think to inline it at the 2 call sites. And now this is the code we would like to see. Right now we just have that, we have it in a loop that's going to return true or false. So, if we wanted to think in CPS and work in ANF, then, how would this look like? What would this look like for the recursive function? So the crucial thing about find that let us quantify it, that made it so that the argument was unchanging and we could do the static argument transformation, is that it's tail recursive, right? The recursive call is a tail call. It's just it's the very last thing that happens. And in CPS terms, that means that the continuation is unchanging. It's not getting any bigger. And you can also see this in direct style. This is going back to direct style. We can see what a tail call is. Well, not everything here was a tail call. Right? So what can we do about that? Well, happily, there's already a pass that GHC does called float in. If we make a bit of room here, we can see that this let binding can just as happily live inside the case analysis. Move it in here. And now we have 2 tail calls. Now we just have the tail call inside the loop and the tail call outside the loop that gets it going. So what can we do with that? So here's the idea, is that we're going to tag the functions that are always tail called, that are called like continuations, and call them join points, would sort of term coming from another way that they arise, which is that these functions typically also happen very often just as shared bits of code that get generated, say, in the case of case transform, when we don't want to duplicate code. You end up with just these sort of functions that are always tail called, and it's nice to have them because they are very quick to call as well. They can just become go-tos. So this is a useful property to know about anyway. Then we're just sort of exposing it. We're saying, okay, let's call these things as join points using a label to introduce them, and it's easy to find them is the other thing to know. That's good to know. It's not hard to find a tail call. There isn't the wrong kind of context in between the declaration and the use. So we can just run a pass that finds them all pretty quickly. And then we don't have to come up with any extra semantics either, because it can work just like function calls. But we have invariants that these jumps, which are just invocations of our join points, only appear in tail position and only fully applied. So they're always tail called. And then the payoff here is that we have a new form of the case of case transform, that we will pull the context into the body of the join point. That the case that was living outside of it, now when we do the case of case, when we do all those normalization steps, we now say that the label should come to the top and the case should come to the inside. And this is how we end up eliminating all eliminating the allocations and loops, just exactly this sort of thing. And so we have new rules sort of to go with all of this that the simplifier has to follow. The first one is, as I said, you pull the context into the body of the join point. Sort of simple as that, and with the same sort of measures as always to help with code duplication. And then since, you're making these things maybe not, the tail calls have to remain tail calls, so the recursive invocations and such. You have to get rid of the context from those, and that's easy enough. You just throw away the context when you see the original jump. And these are both drivable purely from the CPS. If you translate a joining point as simply a continuation, right, as a function that doesn't itself take a continuation argument, then simple substitution, beta reduction, gives you both of them, because the body of the function will have of the join pipe will have a reference to the outer continuation, and the jump won't have a reference to the variable. Both of these just in substitution will apply. And so the application that you can get from this is to list fusion as one happy result from this. And so here we have, this sort of comes from, for example, this is the standard unfold function here. We represent lists as functions that will take some sort of seed value and keep producing new ones. It keeps, the stepper function takes this state and says, okay, here's an argument, and it either says we're done, or it says here's an element and here's the next state. And then we recursively keep on doing this. This is one version of list fusion, of course. What's good here is that now if you write your list functions as steppers, list operations as stepper functions like this, they get to be composable, right? This is the fusion-friendly version of filter that all it does is, each time through it'll ask it asks whatever it's filtering for the next element, and if it returns something that meets our predicate, it returns that thing with the new state. Otherwise, it says nope, keep looking. It loops. This is actually very similar to the any function we were looking at before. And if it's done, it's done. If it's done, the filter is also done. And this works. You can write this does, you can compose several functions together, and it doesn't, the point of fusion is, of course, that you don't produce intermediate lists, right? If I just write a filter of a filter of a filter of a filter, and every one of those is actually producing the intermediate lists, you're wasting a lot of code. If we use list fusion this way with filters, you do at least get rid of those lists, right? That's an improvement. But now you have this just and nothing cruft sitting around, and there isn't any obvious way, before to deal with it. We don't, the case of case works great for functions like map. Will happily, pull the case inward and eliminate the just and nothing. But with filter, you have this inner recursive loop, and it gets in the way. And you can see what happens here when you think of composing unfold with filter, because here you have an inner loop and an outer loop, and just as before we had the returning true or false depending on the just or nothing. It was a similar situation, only it's another loop, but it's the same sort of thing. The seek function is either going to return just and then definitely go to the just branch, or it's going to return nothing and definitely go to the other branch, or it might loop back again. There's just no, as humans we can see this, but the compiler hasn't been taught about this. But in the branch, with the new case of case transform, they fuse nicely. because the case gets pulled inside the seek function, and then everything cancels, and you sort of have the code, something that looks a little bit like the code you might have written. You wouldn't necessarily have used, the little inner loop, but there isn't any more, no extra values are getting created anymore. And yes, in extreme cases, if in some of the benchmarks, there are loops where the only thing that happens is the only allocation that happens is one of these values that can now be taken away. So the reason you get kind of eye-popping benchmarks is just that there's no per loop allocation anymore. We get through the whole loop. So if we run it 1 million times, we've now eliminated all of those allocations. So, and you can play with this. It's all in this new branch of GHC. The one nice thing about it was it did not take any big changes to the core intermediate representation. It was mostly a matter of adding a field that says this is a join point or this isn't. And then the simplifier now does the case of case, as I was showing it, with pulling the context into the join point end of the body. And then the other passes I'll have to respect the new invariant as well. But as IR changes go, this wasn't radical, so it was pretty good. I would say bang for the buck. So, are there any questions? Yeah.
You mentioned if you have a sequence of ASCII filters that you can sort of use lists. If you follow that by default, can you get rid of the intermediate list altogether?
Oh yeah. I mean, and that's a standard. That's not new here. But yes, if you start with something that generates numbers, a list of numbers, and then things that mess with them, and then something that consumes them, then you'll never have a list. Yep.
So you've taken one CPS idea and introduced a new feature to ANF for it. When will you know that you're done?
I mean, I don't think I would necessarily. I mean, I think it's good to have this sort of, language that's sitting there sort of behind the scenes, kind of, that describes what's going on. And in fact, I've sort of been using CPS for an example, but we're actually using the sequent calculus as that. It's a little bit sort of more kind of basic from our, some sort of nice properties. But part of the idea here is just that you don't actually have to be implementing things in the language that you're reasoning about.
Can I have another response very quickly? So in some sense, optimizers are never done, right? But I now don't know of any transformations, any optimizing transformations you can smoothly get in CPS or in sequent calculus that you can't get in direct style with this. So I would love, if there are any, I'd like to know. But I wish I could prove that there were not, but I don't know how to do that either.
Can I go back to the performance numbers?
Oh, yes.
Yeah, so why is there a case where spectra are norm?
As I recall, this was something is getting inlined that sort of unfortunately. One of the tricky parts about about working on the GHC optimizer is that basically anything you do could go wrong because you might make some function smaller, which is good, but then it gets inlined into some other function that makes it bigger, and now it can't be inlined into somewhere else, right? So as I recall, it's one of those cases where, no good deed goes unpunished. And yeah, I mean, it's pretty difficult to write anything that doesn't go wrong in some way, just because of the way that GHC runs the simplifier so many times at different points, and everything gets a chance to interact with everything else, which is a good thing, but it does make things sort of harder to, it means you have to take your lumps sometimes. Yep.
So you didn't say anything about SSA. I was wondering, the obvious connections, fire functions.
Oh, yes, yeah, no, that's definitely, yes. So yeah, join point is definitely, you can definitely see that as a phi function. I mean, especially in those sort of, just the way that SSA and CPS are kind of mirror universe versions of each other. But yeah, no, that's definitely, if you wrote things out, if there's sort of also a way to relate SSA to A and F, and then it looks very much like what we're looking at. So yeah, no, definitely, that's a cosmology.
Describing what you've done and giving sort of rational reconstruction of one of the aspects of SSA.
Yeah.
Like 5 functions.
Yeah,
that's
that's
what
what I'm saying.
Yeah. I would only, it feels like I would be taking credit for previous work, because, the connection has been explored. But yes, no, it's definitely there.
Okay, let's